Good evening, everyone. Am I audible? Am I audible?
Yes, sir.
Okay, thank you. So let's wait for 5 minutes and after that we will start. So my screen is visible, I think. Please confirm that my screen is and my pointer is visible. So how many are new today? Like anyone is having like your first class or second class? Anyone? Or are you regularly attending these classes?
Hello, sir.
Yes.
Yes, sir. It would be my second class about Aspen, like regarding the doubt solving sessions.
Okay, it's a second class. Okay.
Yes.
So like in a row or like you joined like in the week first or second or like you
I
were in previous
joined
class.
the course in the third week,
Okay,
so I watched the recordings provided by professor.
okay. Okay, I think 5 minutes are over and we can start. So good evening everyone. I welcome you all to live session for Aspen Plus Simulation Software, a basic course for beginners from NPTEL. The course instructor is Professor Praveen Kumar Shah from IIT Guwahati and I'm his TA Amit Kumar Sharma. So every week on Sunday from 7 to 9, we are having a live session. So in this session, we discuss like a summary of previous classes in that particular week. And we also solve some simple question from previous year assignments. So the motive of this class are to uh, to show you that how to solve the assignment question and what should be the approach and what type of question can be in the assignments. And the other important thing is that this meeting is being recorded, and the meeting recording, like this complete video, and the PPT will be shared to you from the NPTEL team. So those who are not able to join today, maybe they can refer to the recording. And if you, I think you all have Aspen Plus installed in your system. So I request you all, please start that software, because in today's class we are going to do some assignment questions. So in those questions, you need to do those in the Aspen Plus. So be ready with your Aspen. So in class, first we will go through summary of the week 4 class notes, and then we will start the assignment questions. Okay, let's begin.
Hello, sir.
Yes.
Actually, I'm unable to download the Aspen Plus software using the links you have provided. So, in the last class, when one of the members were telling about this problem, you said we can discuss in the WhatsApp group among the members. So, I do not know what the members are having. So, can any one of the members can share, or if you have?
Actually, I don't have those information. So any of you, if you have, please share share this information on the chat box. Maybe anyone, if want, can refer to that. And the main thing is that if you are not able to download the software, so I advise you should email to the NPTEL team. So you should, yeah. I think they have also shared a form, so you can fill out that form, and they have shared multiple links. I think they have shared multiple emails with multiple links. So maybe you should try a different link, and they have also given a complete document for the installation. So go through that. And recently, I think they have shared the Aspen version 14, the link for version 14, I think. So if your previous link is not working, you can try version 14 also, the recent link that they have shared. And if you still face the problem, then you should draft an email to the NPTEL team. Okay. Anyone else? Like anyone else is having any doubt? Because now we need Aspen actually. So the Aspen should be in your system. Okay. So in previous week, we have discussed about the property analysis. So like as of now, like we were doing some like direct modeling of components. We were looking into how to use the component models, how to use different properties, but we were not we have not seen the complete detail about the property analysis. So in the previous week, we have covered about the process and property analysis. In that, the usefulness of Aspen Plus in modeling like physical properties, then the model of pure binary, ternary, and multiple mixer systems, then to understand and select the relevant property method. So these things we will cover in we have covered in the previous week, and today we will summarize this very quickly. Then the ideal model, equation of state models, activity coefficient models, special models, then like some parameter regarding pure binary and ternary parameters, then the plot relevant data. Okay. Then the manipulation of raw and theoretical experiment data via regression. So basically, like if you have the experimental data, then you can use some property methods to see that is your method is like giving the same result like as the experiment. So you can do a comparison. Then the NIST thermodata engine and the DKMA. So it is, I think, the paid one. And this one is the inbuilt in the Aspen. And the reporting relevant results like property sets, then the table, charts, graphs, plots, and model fitting. So these are the things that we are going to cover. So for these things, you should know basic like chemical engineering basics, then the physical chemistry, transport phenomena, process and equilibrium thermodynamics. Okay. And the select suitable property method correctly and set a physical property environment for process simulation. So actually the importance of property method is very important. Okay. So suppose now I think from the 3 weeks, you all know how to model reactors, how to model like uh, like compressors, turbines, okay, how to model like distillation units and all. And we have seen one complete process modeling also. In that we were having different components, but if you don't select the correct property, then the results from those components will be not good. Okay. So you can have like sometimes the deviation is not that significant, but sometime if your property you have not selected a proper property, and like you have like there are some binary parameters also, if you have not selected the binary correlation correctly, so in that case you are having like a significant difference in the results, and based on those results you cannot design your system properly. Okay. So basically you cannot design a system properly, you cannot optimize the efficiency, you cannot optimize the cost. So the purpose of a suitable property method is very important. You should know how to select a proper property for your system. Okay. And how to select like the all the like the parameters, like because in property we can set multiple parameters and all, because and when you have a complex system, then if you don't have all the arrangements of your components and your properties, then it will be difficult to analyze this complete result actually. So in this view, we will also cover how we make a group of some components so we can easily see the results and all. So the free water versus the dirty water. So in the Aspen, the Aspen properties can handle the presence of decanting of pure water, that is free water, as a second liquid phase in water hydrocarbon and other water organic systems. So free water is like pure water, and dirty water, it have some trace component amount of hydrocarbons. Okay. In the water decanted as a second liquid phase. Then the Henry component is very important. The amount of supercritical component or a light non-condensable gas such as CO2, N2, O2, CH4, etc. in the liquid phase. So these are the Henry components. And the Aspen Plus has extensive collection of Henry constant for many solutes in the solvents. So we have already defined Henry components in Aspen Plus. These are used with the idle and activity coefficient models such as NRTL, Unifac, Uniquake, Van Laar, and Wilson. So these are some models in which we use the Henry constants. Then the Henry constant model parameter must be available for the solute with at least one solvent. So it should be available for the solute with at least one solvent such as water, ethanol, acetone. So we have some solvents, so at least one solvent should be there. Okay. So you can see it's like a straight line. For more detail regarding this, you can refer to the class note or a reference book on Henry's constant. So the example is set Henry's component parameter for a system with condensable water, ethanol, and acetone, and non-condensable carbon dioxide, nitrogen, oxygen, methane. Use NRTL property method. So this type of example you can try. Professor has also shown in the class. So you have to use the NRTL methods. Okay, you have given the components like the water, ethanol, and acetone, and the carbon dioxide, nitrogen, oxygen, and methane. So just select the components all in the Aspen, then this method, and then do the calculation. So now we have different component types in Aspen. So if you have seen the Aspen window, then you have seen the component types. So we have conventional, so solids, non-conventional, pseudo components like SA, blend, polymer, hypothetical liquid. So normally we use the conventional. If you don't change it by default, the Aspen select normally conventional. So it's single species fluid, vapor, or liquid. Typical components that may participate in vapor liquid phase equilibrium. So if you try to enter a component most of it will be conventional type automatic selected. If you want like solid, then you have to change it. The solid is single species solids properties are calculated by the solid based model. So suppose if you are defining a component in solid, then the properties will be like all the properties selected from the Aspen will be for that particular range only, like for solid component only. If you define the conventional, then it will consider vapor and liquid. So the properties that will be used in your modeling will be as per this. Non-conventional solids that are not pure chemical species, they are not represented as molecular components such as coal or wood pulp. They are characterized using component attributes and do not participate in a chemical or phase equilibrium. So we can also define non-conventional. Then similarly, like pseudo component. So these represent petroleum fractions characterized by boiling point, molecular weight, specific gravity, and other properties. In the polymer, oligomer, and segment, like components used in polymer models, then hypothetical liquid. So a component type that is mainly used in pyrometallurgical application when modeling a component as liquid, when its properties should be extrapolated from the solid properties. For example, modeling the carbon in molten steel. So let's go to the Aspen and quickly see where can we find these types of components. Is my screen visible?
Yes.
Okay. Just open a new document. So here normally we enter a component. Suppose we enter methane. So if you type CH4 and press enter, then it will automatically select type conventional. So here you can see the type. So this is the type that we are discussing. So if you look at here, so we have like conventional, solid, non-conventional. Okay. So if it's by default conventional, then it will consider vapor or liquid. And the properties, all the properties, temperature, all the like other thermodynamic properties, all properties will be based on this conventional only. If you go back to the Aspen, then you can change it. Okay, like solid, you can change as per your component. So basically, methane is conventional. Okay, if suppose you have only carbon, then carbon is like a graphite form. Okay, but it is taking it conventional. So basically, I'm talking about solid carbon because sometimes when we are having reforming reaction, okay, so there will be some carbon deposition due to methane cracking, due to Bourdon reaction. So there are different reactions. Due to that, your methane can be like converted into carbon. Okay, so then you should select it. It's solid. Okay, so you can change it to solid. Like suppose silver. So it is also coming as conventional, but you should change it to solid, because if you change it correctly, then all the properties, all the parameters will be as per this type. So it's really important. So we have options here like solid, non-conventional, SA, blend, polymer, like all different types of types we have here. So these are the types. Then the component group. So a component group consists of either a list of components. So we can make a component group in which we can define list of components, range of components from the component list, combination of lists and ranges. Okay. So basically, suppose you have some components like in the liquid form, and some will be in the, suppose they will be always be in the gas form. So you can define different components like, so you can make two sets, like one will be condensed and one will be like in the vapor phase. Okay, So you can define these. You can define some components, like suppose component A, B will be in this group, C, D will be in this group. Okay. So you can define by those. You can define the range of components from the components list. Suppose you have multiple components A to X. Okay. Then suppose if you want to select B to X whole component, you can only directly define B to X, so that all the components between B to X will be selected in a particular component group. Then the combination of list and ranges, so you can define the list or you can define range both. A component may appear in more than one group, so like there are three groups, so the C can be in this group also, and also it can be in this group like C, E, F. So C can be in multiple groups, like other components are also in multiple groups. So what are the advantages? So it helps in the tier stream convergence and recycle loops. Handling is easy when number of components is large. The grouping helps for some components known to have zero or constant flow rates. So like it's really helpful for some components known to have zero or constant flow rates. Then the plot composition and k-value profile of groups of components in distillation and reactor model. So if you have already all like particular groups, then it will be very easy to analyze the results quickly and effectively. Then we have different databases, okay, like pure 37, inorganic, aqueous, solid, etc. preceded by APV 110. So the point is that this APP V110 is basically it's mean Aspen plus Aspen P plus V version 11.0. So basically it define the Aspen plus version. Okay, so suppose if you are using 14th version, then it will be APV 140 like that. The content of this database are continually updated, expanded, and improved. So like we have seen, like frequently we receive update from the Aspen, so they update the database. Okay, they expand database and they improve it. It is based the data developed by the DIPPR, Design Institute for Physical Properties. Data compilation project, parameter developed by Aspen Tech, parameter obtained from Aspen CD data bank and other sources. So there are different sources. Some are mentioned here. All over the world, various research are going on. So from those researches, different data banks are there, different R&D institutes are there. So they develop data, and now based on those, they update it. So in the class, professor discussed like create a component group, add components, then how to prioritize a particular data bank such as ethylene data bank. So quickly, if you want to see it. So suppose we have a benzene. So here you can see the databases actually. So you see I am using the version 12, so it is APV 120. Okay, and these are the database. So suppose if you want to add the ethylene, okay, so let's find ethylene. Let me type the name exactly. What is the name? ETHYLENE. Okay, so here you can see that. So we have ethylene and data bank is pure APV 120. So Aspen plus version 12 and pure 38. So this is a data bank. But suppose if I want to use, so if you select it, so it will take this ethylene from this data bank. But now you want to select this, we have already available data banks and we have this data bank, okay? A proper data bank for ethylene. So just select it, then move it to right. So you can increase the priority. So the priority starts from here, top to bottom. So now you can see here earlier the APB 120 pure 38 was at spot 1. But now the ethylene is at spot 1. So now if you go to the component ID and if you find the ethylene, then see it will. So see, the data bank has been changed. So earlier it was APV 120 pure 23, but now it is coming from this data bank. So in this way, you can.
Sir, what will be the difference between the two, means selecting from the ethylene data bank or pure 38 data bank?
So actually data banks are having, like, if you want to study about it more, so you should go to the reference section. But like each data bank have some properties may be slightly different. So they have, these data bank are developed, okay? So as I earlier told you, like various researchers, like all over the world, many institutes are there. So they're developing the data banks. They are continuously updating the software and all. So these databases are continuously updated, expanded, and improved. So maybe suppose if you are using the particular ethylene database, maybe so that particular database, maybe the accuracy is more, maybe like some parameters are like significantly like defined up to like high up to higher accuracy maybe. So I don't know the exactly, but there will be some difference. That's why, because if
So
you yeah.
every component will have its own data bank. Like for ethylene, we selected from the ethylene data bank. So for any
So
component, we can select its own data bank.
no. Every component don't have a separate data bank. Some components have. Like we can see the data banks for polymer. So polymer is including a complete range. Okay.
Hmm.
Like suppose we are also having some pure 2.5, pure 2.6. So you need to read more about these data banks if you want to. Then we have like biodiesel. So if you are working with biodiesels, then we have a separate data bank for biodiesels. Combust.
Like
So we
all
have data
these
bank
are
for.
general, but ethylene is a very specific component. That's why I was asking.
Yeah. That's why. Yeah, that's why. So maybe the ethylene is having some properties. So that's why they have specified the complete data bank for the ethylene.
Mhm.
Yeah. So you can take help from a reference book, because I'm also not aware what the difference in the properties. But if we have a separate data bank, it means that the all the parameters and properties from this data bank will be more accurately defined. You can say that, like with more accuracy, maybe uh, some interaction parameter and some different properties, like for the advanced user, because we are only doing the basic modeling. But when we are doing like rigorous modeling, advanced modeling, we are like suppose we are developing our own model. Maybe in that case, we want to use the separate ethylene data bank.
Mhm.
Okay. So the point is that you have different data banks. You can select as per your choice. So after I think this course, you will get to know a overall like how to use the Aspen and all the things. Then when you go for your own modelings, then based on your research problems, then you will be, I think, get knowledge about these things. And always there is a help section. So if you are having any doubt, go to the help. Then you can search here, type the data bank name. You will get all the detail, like what is the difference in the pure 2.3 or pure 2.7 data bank and the ethylene data bank. So it will give you a more comprehensive picture.
Okay.
Okay, so like this, we have some other options here. Okay. So like here is the component groups. So you can define a group, okay, like group 1. Then we have these components available, okay. So suppose I want to make a group of methane and carbon. So now they will come into a group, okay. Now I can also select via range. So suppose like methane gets already entered. Okay, so now the AG to ethylene. So we have defined a range from this to this. So all the components will be in a group. Okay, so here you can see the component group section. You can see the so here we have seen the database. Okay. Okay. So like this APV V110 pure 37. So these are some details regarding this database. So it's give you the liquid vapor parameters. Okay. It defines universal constants such as critical temperature and pressure. So these are the basic things that a database contain. So maybe the database that was for the ethylene, the database have some more detail regarding the ethylene. Okay. Like the temperature and property transition, like boiling point and triple points, then the reference state properties, enthalpy, gives free energy, then the coefficient of temperature dependent thermodynamic properties, like vapor pressure of a liquid and all, the coefficients for temperature dependent transport properties, okay, then safety properties like flash point, flammability limits, then the functional group information for unified models, like parameters for RKS and Peng-Robinson equation of states, petroleum related properties like API gravity, octane numbers, aromatic content, hydrogen content, sulfur content, other model specific parameter like Rakan and unique parameters. So in this database, these types of things are defined. Now we have APV 110 aqueous. So this aqueous is used for electrolyte applications. The key parameters are the aqueous heat and Gibbs free energy of formation and aqueous phase heat capacity at infinite dilution. So if you're working with these types of like electrolytes, then you need to select this database. The key parameters in this database is these two. Like the solids, APV 110 solids, then this data bank is used for solids and electrolytes, applications such as NaCl, okay, table salt. This data bank is largely suppressed by the inorganic data bank, but it is still essential for electrolyte application. AP110 inorganic, it contains thermochemical data for inorganic components, the key data like enthalpy, entropy, and all. And for the given component, there can be data for a number of solid phases, liquid phase, and the ideal gas phase. The same set of parameters are used to calculate enthalpy, entropy, Gibbs free energy, and heat capacity for a given phase over a given temperature range. So basically, these data banks have all the details regarding the thermodynamic properties, the temperature ranges, all other properties. Okay. Now the process and property analysis. So, okay, I think we have covered this. So let's see. So what is the property method? So the property method is the collection of models and methods used for calculating the physical properties of components. So we have earlier, we were selecting like NRTL method, Peng-Robinson method, okay, RK method. So we have different methods, but what is a property method? Okay. So the property method is a collection of models and methods used for calculating the physical properties. So basically, we are working with some components, okay? we have to do the mass balance, energy balance, momentum balance. Okay. So basically we are working with the chemical equilibrium and phase equilibrium. So we need to know some basic properties regarding those components. So these property methods that we define, those property methods have they have some models, they have some equations, they have some relations, they have some database. Okay. So like they have some that comes with the database, and also they are taking properties from that and they are using those properties, those data. So basically the transfer properties like diffusion coefficient, heat, thermal conductivity, convective heat, transfer coefficients, momentum, surface tension, viscosity. Okay. Thermodynamic properties like physical properties cover density, molecular weight, enthalpy, entropy, Gibbs free energy, and the phase equilibrium like fugacity coefficient, chemical potential, and K value. So these are the things the property contains, and the properties are calculated through K method, equation of states, interaction in real solution, pure component parameters and binary parameters, activity methods, special system. Okay, steam, amines model, and Grayson solids. So what is a method versus model? So method is a set of models. Okay, and what is the model? Model is a set of equations. So a method have multiple models. Okay, so suppose a method have multiple models. So in each model there will be different equations. Like for thermodynamic model, we have equation of states, activity, vapor pressure, liquid fugacity, heat for vaporization, molar volume density, like that. For transport models, we have viscosity, thermal conductivity, diffusivity, surface tension. For non-conventional models, general enthalpy and density model for charcoal. So these are the models, but in a method, maybe these all three models are there. Okay. So a method is a set of models in which different models have their own different equations in order to obtain the required properties for the components that you have specified earlier. So Aspen Plus has property method which contain thermodynamic models which are very commonly used. So the user can modify the existing property. So we have already some predefined property methods. Okay, we can modify those property methods. We can also define our property method. So like we can copy a particular property method, we can modify that existing property method based on our requirement. So choice of appropriate property method is definitely the prime issue in determining the accuracy of one's simulation results. The property method choice is very important. Okay. So sometimes you will have significantly different result if you change the property method. So suppose the ideal gas and ideal solution, then the ideal model, there are no interactions. If the ideal gas and real solution, then activity coefficient based model should be used. Then there will be polar liquid interaction. Real gas ideal solution, then equation of state based model should be used. Then there will be real gas interaction, non-polar liquid interaction. If you're working with real gas real solution, then the predictive model should be used. Liquid as well as real gas interaction should be considered. Suppose you are having the real gas and real solution, and you are using the ideal model. So suppose this model don't include any interaction. Okay, but here you want to have interactions, otherwise you will not have the correct result. So you need to use the predictive models. Okay. Now the ideal system behavior. Give me a moment. So the so the ideal system behavior follows ideal gas law. PV equals to nRT. Then the small deviation is allowed. Low pressure, high temperature. Very dilute solution follows Rolle's law and Henry's law. Non-polar components with similar size and shape. Okay. Negligible intermolecular interactions. ideal activity coefficient model for the liquid phase, viscosity coefficient equal to 1, activity coefficient equal to 1, is identified with the property analysis plots. Okay. So this is this was the example. It was discussed in the class. So it's a vapor liquid equilibrium for benzene toluene binary system. So these are data from a paper, from this paper. Okay. And you can see the YX like the benzene toluene binary solution. So you can see the relation. Okay. So these are the data for this graph, X and Y. So if you go into the Aspen and if you see, then I think we should get this data. So let's try this. So let's go to the Aspen. So we have given benzene and toluene. Select benzene, toluene. Okay. Then next. Then let's select the idle method. So then if you see here the binary, okay, here you can see, you can select the type, what kind of analysis you want to do, the TXY, PXY, okay, you can see it. Then the component 1, the benzene, toluene, then vary should be the benzene, okay. Then the start point 0 to 1, the number of intervals you can change it. Okay, you can define the pressure here. Then just do the analysis. So here you can see the graph. Okay. If you want to again go to the plot, then if you change here, PXY, so you have different types of systems here. Okay. If I change it to earlier like temperature and XY, and suppose now we use this one. Okay. So you can see the interactions. So if I again if I change here to the toluene, then you can see this kind of results. So basically we can do this, and if you compare, and similarly we can also do for water and phenol systems. Okay. And if you, these are the experimental results. So if you compare the experimental results, you compare the experimental results, so they will be very near with the Aspen results. Okay. So in the class, I think professor has discussed, so you can refer the class videos for further details. So similarly, we can also see for water and phenol binary system. And for this system, I think if we use the idle method, then it will not, the Aspen will not show you the exact result. There will be some deviation. So as I remember, I think this will become like at this point. Okay, maybe we will see in the further slides if I have included those slides. I don't remember. Let's see. So the point is that we have predefined methods in the Aspen and we can do the experiment. So when you do the experiments, so that so the point of the modeling software is Aspen software is that basically we can predict we can, like, if we change the composition, we can change all the things, we can predict the results. We don't have to do the experiments. That is like our aim. Okay, so basically you have to define the method such that if you use the same those components and the same, like you will do the equilibrium calculation, so the results from those methods should be similar to the experimental result, because experiments are the final, actually the exact result. Okay, because in the modeling we are not having exact result, we are having results near to the experiment. Okay, if you want to validate our model, then we have to do the validation with the experiment only. So for this benzene toluene, the result from the Aspen with the idle method is almost similar. Okay, so basically for the benzene toluene, you can use the Aspen with idle method. But for the water phenol system, I think you will not get the exact result. You can refer the class notes for more detail. So for this, you need to change your property method. Maybe from a different property method, you will have the exact result, but you will have some deviation, like this deviation with the idle method if you use the water and phenol binary system. So the applicability of few activity coefficient based model. So what are the applicabilities? So the application, so we have these models: Margulis, Van Laar, Wilson, NRTL, Uniquac. For the binary system, they all can be used. Okay. So the multi-component, the Margulis and Van Laar are limited, but the Wilson and the NRTL, Uniquac, yes. Azeotropic systems, all yes. Then if you come to the dilute system, then we don't know. Okay, and they can be used. The Wilson and RTL unique case will be used. Like for the polymers, no. Extrapolation are possible with the Wilson, good, and good. So we have some applicability of your activity coefficient based models. Okay, these are the relations. And if you see the star mark is there, so in the NRTL, the binary parameters are regressed using vapor liquid equilibrium, liquid equilibrium data from the Dortmund data bank. So in this NRTL, if you are having the binary parameters, they are regressed using these two equilibriums data from this particular data bank. Then what are the recommendations? So we have some recommendation, like for non-polar system, you should, all the models will yield reliable data. So if you are dealing with the non-polar plus non-polar system, then you can choose any model. Most of the model will yield the reliable data. If you are having non-polar and weakly polar systems, then all models are good. However, Uniquac model is the better than others. Maybe the deviation is only maybe the 1%, 0.5%, but they are good, and the Uniquac will give you the better result. If you are non-polar and strongly polar, then the Wilson model is the best. Okay. The weakly polar, then Uniquac is the better. Then the weakly polar, strongly polar Uniquac is better than others. Strongly polar than Uniquac. Aqueous solution, of a strongly polar component unique, and the aqueous solution of a weak polar and non-polar component. So none of these models work due to poor limited solubility. So it's important. So like if you have these kind of system, then these models will not work. And the reason for that is that limited solubility. The solution with carboxylic acid, the Wilson model is the best if the components are mutually soluble. Solution containing polymers use Florey-Hugginson model. And a solution containing strong acids then use Debye-Huckel model. Multi-component mixture model has to be chosen based on the dominant component in the mixture. So these are some recommendations. So based on like the experience and all things, the comparison with the experimental data with the model with different components, these are the recommendations. So you can see clearly that each model is not applicable to all the systems, all the conditions. Okay. So for different conditions, we have different models that will give you significantly more accurate results. So it's very important to first understand your system clearly. Okay. What kind of components you are having, what kind of relation will be there, what kind of properties calculation you need. So based on that, you will define the model and the property method clearly. And the UNIFAC model, so UNIFAC functional group activity coefficient model, it's semi-empirical model to predict non-electrolyte activity in non-idle mixture. So basically UNIFAC model predict, okay, non-electrolyte activity in non-idle mixture. Use functional group in the liquid solution to calculate the activity coefficient. It is group contribution model, hence it is predictive in nature. So important, like what kind of UNIFAC model is. So it is a predictive in a nature. So it can be a question in your assignments like that. So good approximation method for missing pairwise interaction parameters, like in some calculation, we don't have all the interaction parameter with, okay. So if we, I think in previous classes also, for some systems, we have done the property estimation using UNIFAC estimation. Okay, so if we select the UNIFAC estimation, then there will be more binary parameter interaction. Okay, so you are having the good result, the exact result. So because if otherwise you are missing some interaction parameters, so the results will be different. Then it uses property constant estimation, PCES regression, that provides a Bondi method which requires only molecular structure as input, and use experiment data if more accuracy is required. So it's better to use experiment data if you want more accuracy. So these are the from this paper. Okay. So there's an example. So the comparative study of flashing equimolar mixture of water, hexene, phenol, and benzene. So we have given these equimolar mixtures. Temperature we have given, at atmospheric pressure we have given, and you need to use, and we have to use the models idle, Vanlar, Wilson, NRTL, UNIQUAC, and then use UNIFAC to find missing parameters. So this is a table. So it's giving you a basic results comparison of all the models. So if you use, I think the professor has already solved this question in the class. You can also try it. So basically, if you select these components and you select the idle model and equimolar mixture, basically, so we have 4 components: water, hexane, phenol, benzene. So let's say each component is 25. Total feed will be 100. So if you use the idle model, then the vapor fraction will be 50.808. The liquid fraction will be 49.19. Okay, and if you use 1 lar, then the vapor fraction will be 48, liquid will be 51. So see, there is a difference. Okay, from 50 to 48. Then if you use Wilson, then 66. So if you compare the idle and one-lar, so the difference is not that significant. Maybe you can ignore this, but sometimes this difference is also very big. But if you compare the idle and Wilson, then it's huge difference: 50 to 66 and 49 to 30. 50. Earlier, like you were having 49 of liquid mole fraction, but now you have only 33.8. So it's a really significant difference. If you use the NRTL, then the 73 and 26. Again, the huge difference from the idle. Uniquac 74 and 25. Unifac 73.44 and 26.559. So the meaning of to show you this comparison is that the selection of model based on the component is very important, and what kind of process you are choosing for your component. Like here we are doing the flashing, okay, at this particular temperature and pressure. So basically we are converting the vapor, we are separating the vapor and liquid part. So it's really important to select the proper method. So otherwise you will have different results. So you can see here, or there is a significant difference. So in the idle, you have 50 fraction of vapor, and in the unifac you have 73 fraction of mole fraction of vapor. Okay, so almost how much? How much difference is there? Almost 50%. Okay, so almost you can say like 47 or 50% difference is there. Now the equation of state-based models for vapor mixtures. So if we have vapor mixtures, then normally we typical models are Peng Robinson, Sovek Redlich Quang, okay, SRK, and the Lee Kessler Pokler LKP. So low pressure with no associating components, assume idle gas mixtures. So you use these models on like these conditions. Low pressure containing associating components, slightly elevated pressures for vapor mixture containing hydrocarbons, inorganic gases, but not HF. And elevated pressure for vapor mixture containing one or more polar or associating components. Okay. Use Frank Robinson and SRK with excess Gibbs energy based mixing rules and appropriate activity coefficient model. So we have a small example. We can try this. Like comparative study of flashing equimolar mixture of C1 to C5 at 120 degree and 50 atmospheric pressure for the models idle, LKP, SRK, and PR. So please try this. You have 5 minutes. Quickly. So you need to select C1 to C5 components. So CH4, C2, H6, C3, H8, C4, H10, and C5, H12. Temperature you have given, the pressure you have given, you need to select these models and you need to compare the results. So, anybody is trying?
So can you open the question page once more?
You need to select these components, the temperature, the pressure, the models idle, LKP, SRK, and PR. This is the question. So you can select the component like this: methane, C2H6, C3H8, butane, and pentane. You have 5 minutes. Try and let me know. If you have seen the question, then I can just show you the components. You can select these components. So you can select first methane, then C2H6, then C3H8. Okay. Then if you type C4H10, so see, it's not taking the component correctly. Okay. So you see here, its component name is not coming, CS number is not coming, so it's basically not taking the component in this form. So you should change it to, what is the component? It will be butane. Okay. Type butane here and press enter, and delete the existing one. So now it's coming here, and butane. So it's like C4H10-1. This is the, so the component in the Aspen database is like written like this. Okay. Similarly for pentane, it's C5H12-1. Okay. So now you have selected the components, then click next. So here you have to select the methods. So go to the question, you have given the idle, LKP, SRK, and PR. So see very carefully. If you see here, so on the left side, we can see the methods, then specification, then the parameters, then the binary interaction parameters list is here. Okay, so you can select multiple methods in one go. Okay, suppose I'm not sure that which method I should use. I have some experimental data. Okay, so each time I don't like, suppose I'm doing a complete modeling. Okay, so I don't have to select the different property method each time for each single run. So first I can select multiple properties, then I can go to my simulation. I will run my simulation and directly I will change the property only in the simulation window itself, and I will get the different results as per that property method calculation. So see how to do this. So suppose first we have to select the idle method. Okay, then type idle. So idle is there, then press enter. Okay, so it is selected. So if you can also see here the selected method. So one, you can see the idle is there and there is blue tick. So the idle method is selected. Now change the method LKP. Then don't click next, don't click run, then just only select the method LKP. So it's LK block. Okay, LKP. Again, it's selected. So now you can see two methods are there, idle and LK flock. Now the other method we have given the SRK. So select SRK. So SRK is there. So if you click it, then you can see here now we have three methods. SRK is also there. So next is Peng Robinson. So where is this Peng Robinson? Yeah. So now you can see here in the right side. Okay, in this you can see methods. And the methods are, we have selected idle, LK block, Peng Robinson, and SRK. So now you can click next. So first it will calculate the binary interaction parameters for this LKPK. Now again click next. Now it will calculate the binary parameters for based on the Peng Robinson. Now it will calculate the binary interaction for the SRK. So basically now we have all the binary interaction based on these methods. Now click next. So it's okay now. So you can run the property analysis. Okay. So property analysis is completed. Now go to the simulation window. Because in the question we have given, we are placing equimolar mixture of these things. Okay. So just select a flash chamber, then provide the input. This is S2 is for the vapor, S3 is for the liquid. Okay. Now we have to give the inputs for the stream. Then next, then it's asking for the S1 input stream. So we have given 120 degree 50 atmospheric pressure. Then select the temperature 120, and the pressure is 50 atmosphere. Okay. Then we have given the equimolar. So we have 5 components. So let's make it 20 each. Okay, because we have to make it 100. 20 each. Okay, so let me just tell you again that here we are selecting the composition mole flow and the unit is kilomole per hour. So if I'm writing 20 20 20 mean each component is at 20 kilomole per hour flow rate. I can also define by mentioning a complete flow rate 100 here. Then I will select mole fraction here. I type it 0.2 0.2 0.2 0.2 like that. So I can also do in that way also. Okay. Now you define all the parameters. The tick is okay. Click next. Now for the flash chamber, just Duty select duty 0 we have not given. We have given the pressure. That is how much is given? 50 atmosphere. So 50. Okay, it's okay. And next. And click run. Okay. So the results are available. Now you go to the stream results. Then you can see the results here. So if we go to the mole fraction, okay, then we have the S2 was the vapor and S3 was the liquid. So we have 87.49 and 12.50. Okay. So yeah. So now we can see that 87.49 and 12.5. So these are data for Peng Robinson. But we have selected 4 methods. But how do we know that this method is which method is currently using? So for that, you can go to the block option. Okay, so block B1 is the flash. If you go to the block option, then here you can see the property method. So this block B1, that is the flash, it working on this method. So currently we are having the result based on the Peng Robinson. So you have to see the Peng Robinson. So we are matching the result. Now, if you change the method directly here, because in the property analysis we have already defined 4 methods. Now you have to change it here only. So just change it to the idle. So this method is already defined in the property. So don't worry, directly run it. Yeah, so results are available. Go to the stream results. Then you can see here the mole fraction. Yeah, it's 64 and 35. So 64 and 35. So that is for the idle. Okay. So now you can see the difference. There is a significant difference. So you need to be careful which method you have to choose. So basically, again, you can go to the block option. You can change the method. The other when we have defined the SRK. So find the SRK. SRK is there. Again, run it. Go to the results. Then you can see the SRK results. Okay. So SRK is 85 and 14.3. 85.6 and 14.4. Similar to that. So these are the methods. In this way, we can do the things. Is it clear? Any doubt regarding this? Okay. So now let's start with the. So we also have some special systems like amine electrolytes, ENRTL method with RK equation of state, amine property package, then the petrochemicals, steam water, steam table, steam NBS, and IAPWS 95 is very famous now we are using this nowadays. And also we have some property method for gas processing units. So if you are working with hydrocarbon separation, demethanizer, C3 splitter, Peng Robinson, BM, SRK, BM, these are the methods. You can refer to the class notes. Okay. The gas dehydration with glycol, PRWS, SRKWS, like that. For the acid gas adsorption, elect NRTL, then the closed process, then PRWS, SRKWS, like that. Okay, we have some more methods like ethylene plant, Grayson, then ethylene plant, PR, SRK. So we have given different methods. Okay. So we can also define the root ID and we can also create our own property. Okay. We can define the property paths, physical properties, models. So a method root is the combination of property method and the models which are used to calculate a property. One can view, clone, modify, and create method. So we will look into this by an example. Okay. The property sets, it is the collection of thermodynamic, transport, and other properties used in the physical property tables and analysis. So we can define our own sets, we can change it, we can customize. Aspen Plus has several built-in property sets that can be used for various applications. Each simulation template has its own, so we have different simulation templates. When you start a new simulation, then there are some templates there. You can select a template. Each template has their own built-in property sets that can be used while creating a new run. The property sets can be modified as per the user and as per the use and the need. A few available properties are as follow, like thermodynamic properties of pure component, thermodynamic properties of components in a mixture, okay, like CPMX, MUMX, like that, electrolyte properties and properties related to petroleum products. Now let's start with the questions. Okay, so it's good if you open the Aspen and let's start. So usually the amine systems are dealt with activity coefficient models, equation of state models, ideal model, special models. Take 2 minutes and let me know the answer.
Special models.
Special models. Okay, we have an answer.
Equation of state models or activity coefficient models.
Okay, let's see.
Special models.
Okay, so any special reason for that? What is the reasoning behind your answer?
I've used the Grayson model.
Sorry?
Grayson model.
Okay. So that's why we are using the special models. So yes, the correct answer is the special models. The amine systems are dealt with the special models. So these, like activity coefficient, equation of state, and ideal models, are not relevant to the amine systems. Some special models are there. I think one of you has mentioned one model. So we have to use those models for amine systems. Which among the following is not a standard unit set in Aspen Plus version 12.1?
Second option.
Option 2.
Second option.
Okay.
Option 2.
So let's see. Yes. So option 2 is normally not in the standard unit set in Aspen Plus. Aspen properties uses hydrocarbon solubility model to calculate trace amount of hydrocarbons in the water decanted as a second liquid phase. True or false?
True.
Okay. So I think we have seen in our slides also, like free water and dirty water, I think. Yeah. So one of the dirty water, I think, contains some hydrocarbon also. true or false?
True.
True. Okay, so it's true because it used the hydrocarbon solubility model. Based on that, it will like find like how much hydrocarbons are present with the water, okay, with the decanted stream. So there is a picture, a snapshot you can see here. See it clearly. Okay, the figure 2 is a snapshot of the property estimation run in Aspen Plus. Answer the next two questions. The first is, which among the following is not a Henry's component? CO2, ethane, methanol, and water.
Water.
Okay, we have one answer, water.
Water.
Think about it. Wait for more answers. See this table carefully, actually.
Methanol also.
We have another answer, methanol.
Water.
Any reasoning for water? We have 3 or 4 answers for water.
We can see the source, its binary system, not Henry's component.
Okay. Now, are you using this table or not?
I'm seeing this table, the source.
Okay. The source.
We can see. Yeah.
Where is the source?
So that third column.
Okay. Okay.
We can
Third
see
column source. Okay. So what we have given here?
binary.
Okay. We have given like binary. Okay. So you are looking at like this. Okay. The Henry. Okay. Okay. But which one you are choosing? Because we have component I and component J. So if you see this binary is with component I or component J, you have two, na? CO2 or water. Is it for CO2
Yes.
or water?
In water, not
Why?
CO2. CO2,
Because if
it's
you
a Henry's component. You can see
okay,
that.
okay, let's see. Anybody else want to explain? Because I am not from the
All
chemical
other are some
background, so
non-condensable components.
I am not expert of this Henrys and all components. So
the first column, the component I,
yeah,
that is the Henry component, and the second column, component J, that is the means solvent.
solvent. Correct. Yes. Yeah. This answer it seems correct to me. So we have now
Yeah,
the
that's
methanol
what
and
I
water
said,
both.
methanol and water. Yeah.
Yeah. So I think we need to then the both actually, na? Because if you see only in the component I table, you don't have methanol and water. All other components are there. Like CO2 is there, O2 is there, N2 is there, CO2 is there, ethane is there. So these are like the relation with these component J. Okay, so the component I section don't have methanol and water, and other CO2 and ethanes are there. So these are the Henry's component in relation to these solvents. So the note Henry's components are then the methanol and water. Now, which among the following property method has been used in the property estimation? The same question, the same table, okay? First see the question, then I will go to the table again. Which among the following property methods, so you have given 4 methods, Peng-Robinson, NRTL, SRK, Wilson. So has been used in the property estimation. So which method has been used for the property estimation? NRTL. So we have an answer, NRTL. Let's wait for another answer. Anyone else?
NRTL.
Okay, please explain the reasoning also.
So Henry's law we are using, so it's an
Okay.
ideal model.
Okay. Please explain in detail if you know further. This is the table if you want to see the picture.
So basically, NRTL is used for vapor liquid equilibrium, and here, since we are using Henry's law, we know it's an ideal model. Means we are assuming vapor liquid equilibrium, so that's why.
Okay, nice. So yes, it's NRTL, and as you also discussed it. So the PEF, like this Peng, Robinson, SRK, Wilson, they are mostly for the hydrocarbons and all. Okay. So NRTL is with the Henry's component and these water, methanol, and these components. So now open a new simulation in Aspen Plus. Like, don't worry, it's which version you have in your desktop or your laptop with electrolytes with metric units template in chemicals category. Then answer the following 2 questions. So you have to open a new simulation with electrolytes with metric units template in chemical category. Important. Use this template. Then the questions. Which among the following is already present in the compound list by default? Let me know the answer.
Water.
Okay. Let give 2-3 minutes so everybody can check. I think you all have Aspen in your system. Please go and please open this and let me know the answer. Because we have multiple questions based on this only, like next 4-5 question will be on this only. So please do it. It's consider it like mandatory. Open a new template with the electrolyte in chemicals category and let me know which among the following is already present in the component list by default. As of now, we have received only one answer. Let me check how many students we have. So we are having around 12 students. So I think all of you should answer this.
Where can we select the electrolytes chemical category?
So yeah, it's very important point. So open the Aspen window, then open a new simulation. Okay, in that you will see it clearly when you open it. So just let me help you. You just close first if you have opened already Aspen. So now if you open the Aspen, click on the Aspen Plus. So now you have two options here. Okay, so open. Already like you have like already did some examples and all. You can directly open that. If you have already like previous examples and in your hard disk, you can go to the open, click and find you can browse the path. You can open the local example that Aspen normally gives you. Okay, then you need to go to the new, because if you go to the question, if you see the question, you can see here open a new simulation. So you need to go to the click on new. Now here check it very carefully. The Aspen plus template. So you have these different templates. One is chemicals, then the gas processing, the mining and minerals, then the refinery, then the special chemicals, and the user. You can define your own template. You can also use some different templates here. So as mentioned in the question, open a new simulation in electrolytes with metric units template in chemicals category. So the category is chemical. So the chemical category. Now I think you can do this.
Yes, sir, thank you.
Everybody, quickly. I have only one answer as of now. I have already given you a hint. Let me know quickly.
Water.
Okay, we have two answers.
Water, sir.
3.
Water.
Okay, 4.
Water.
5.
Water.
Okay, 6.
It's water.
Okay. So is anybody facing any issue regarding this? We have received almost 8 answers. Anybody is having any issue? Let me know. So you need to go to the new simulation, then the chemicals, then you have given here like electrolytes with metric units. So unit is also important, okay? So you have to select the electrolytes. Yeah, here the electrolyte is. So, but here we have given the English unit. So you have to select the metric unit. Click on the metric. So now you will see the electrolytes with metric units. Okay. So now
Water.
open it. So if you open it, then in the component you will see this directly already predefined H2O is there. So that was the question. So yes, it is the water. Nice. So which among the following property method has been auto selected by default for the property estimation? So in the same question, like the one that we have did previously in the new simulation, which property method has been auto selected by default for the property estimation? Go to the properties and let me know which property method have been selected automatically. BK10, elect NRTL, Wilson.
So second
Electric
option.
NRTL.
NRTL.
Elect NRTL. Okay. So if you go to the same simulation, okay, then go to the methods, then specification. So here you can see there is already a method select an RTL. You can also see here the selected methods. You click it here, you can see here the elect NRTL is already defined. It's having the blue circle with white sign. Okay. The correct answer is elect NRTL. Now in the same simulation, okay, you have to add the H2SO4 and KOH in the component list and run the property estimation. Then go to the selected methods tab in the properties pane and choose the method. Open the model tab, answer the following question. Which among the following is the default model for the estimation of liquid mixture molar Gibbs free energy? Okay. So we first go through the question again. Follow the steps as given in the question and let me know the answer. Take 2-3 minutes. Sorry.
D, sir. GMXC and RTL.
So we have one answer, GMXC and RTL. Okay. How many of you are there? So we still have 13 now. So I'm waiting for other answers. Jay Jadab, do you want to say something? I can see your hand. Okay.
Hello. Yes, sir.
Yeah. Do you want to say something? I think I can see your hand. You
सर
raised
वो
your hand, I think.
क्वेश्चन था ना उसमें डाउट था तो सर विच अमंग द फॉलोइंग इज नॉट हेनरीज कंपोनेंट में इथेन भी आ सकता है ना सर?
Okay. So we will discuss after these questions. Okay.
Yeah,
So first, maybe you can try this question. So at the end of the
Yes,
class,
yes.
we will go to that question again.
Okay, sir.
Okay. Anybody? We have only one answer as of now. If you are facing problem, let me know. I will show you. If you are trying, then I can wait for 1 or 2 more minutes. It's clearly given. You have to use the same simulation window. Just add 2 more components. Okay. Run the property estimation. Okay. Then go to the selected methods tab. Okay. Then go to the properties pane and then go to the choose method. Then open the models tab and answer the following question. Everything is specified clearly. Just follow it. I'm just last 1 minute.
Sir, can you please again tell the procedure?
Abhishek, your sound is not clear. Please repeat.
Sir, can you please again tell the procedure for doing this question in Aspen Plus window?
Okay, so it's mentioned here. Okay, so let me start it. So
Option
as
D.
you so we have again 2 or 3 answers. Now we have option D. So let's see it. So we have already defined, we have opened, as we have given in previous question, a chemical template. Okay, a chemical template with electrolytes, with metric units. Okay, and now we are in this question. So we have to add 2 components, H2SO4 and KOH. First, go to the components, then add KOH and H2SO4. Okay, you have selected the components, then the question says you have to run it. Run the property estimation. Then just run it. Okay. You can see at the left bottom results available. So you have run it. The results are available from the properties. Okay. Now go to the selected methods tab in the properties pane. So you need to go to the selected method. So here in the properties pane, this is the properties pane you can see. Let me make it bigger. So this one is the properties pane. You can see it. Then go to selected methods. Here the selected method is there. Okay. Then the question says, and choose the method. So here you can see in this pane we have only one method. Click on it. So you have chosen the method. Okay. Now open the models tab. So if you further see it, here we have 3 tabs: roots, models, and comments. Open the models tab. Click on the models. Then you have the question. Answer the following question. Now go to the question. So which among the following is the default model for estimation of liquid mixture molar gives free energy? You need to find the model for liquid mixture molar gives free energy. So if you go to the Aspen again, then you have given the model names. Okay. So if you take your arrow, then you can get the definition. So this is ESRK. So this model is used in activity coefficient property methods. Then there is GMENRTL. Then the electrolyte NRTL activity coefficient model for mixed solvent electrolyte systems. So similarly, we have defined here multiple models. So you have to find out which one of this is for the liquid mixture molar gives free energy. So you have options already. They are all starting with the G. So go to the option, then select with the model name with the G. So we have one here, GMX NRTL. So click on it. Don't click on it. Just take your arrow to this. Then you can see here electrolyte NRTL model for mixed solvent liquid mixture molar gives free energy. So yes, this is the answer. So GMX ENRTL. So GMX ENRTL is for the liquid mixture molar gives free energy. If you see further the name with the G, then if you go to the other options, okay, we have only one option here with the G.
At
Yeah,
TC.
there is also GS0 POL1. It's for polynomial model for solid pure component molar gives free energy using equation. So it's not for that. So yeah, this one is the answer. Yes, anybody want to say something?
Fourth, sir.
Yeah, fourth. So the correct answer is the fourth, GMX NRTL. Is it clear to everybody? Let me know, because it's really important, because next question is also dependent on this. Is it clear?
Yes, sir.
Okay, I think it's clear. Yeah, Jay, please. Jay Jadhav, do you want to ask something?
No, sir.
I
No,
can
sir.
see. I think you need to lower your hand actually. Yeah.
सर वो फोर्थ क्वेश्चन के लिए किया था.
No, I know your question. You can lower it. We will discuss it after the class.
Okay, sir.
Okay. So the next question is that change the model for estimation of liquid mixture molar gives free energy to GLM XOLI. Okay, read it carefully. Change the model for estimation of liquid mixture molar gives free energy to GLM XOLI and rerun the property estimation. Answer the following two questions. So next two questions you have to answer. The first is, which among the following is also an affected property in addition to liquid mixture molar gives free energy? So which among the following is an affected property in addition to liquid mixture molar gives free energy? So when you will change the model for this property, okay, to this one, then it is sure that this property will be affected, because this property is having a model that was GMX ANRTL. Okay, so if you change that model to this GLM XOLI, so basically you are changing some parameters for this property. So this property will be surely affected. But addition to this, some other property will be also affected. So
A.
what is that
Molar
property?
entropy. Liquid mixture molar entropy. Option A.
So we have one answer, liquid mixture molar entropy. Please take 2 minutes. Let me know the other answers. Like anybody else have any other answer, let me know it.
Option A, sir. Option A.
Okay, we have two answers now.
So liquid mixture molar entropy. Option.
Okay, we have three answers.
Option 1.
Okay, we have four answers. One more and then we will discuss it. Anybody?
Option A.
Okay, nice. So if you go to that same, then if you change this GMXNRTL to GLM XOLI, click on it. Okay, so basically you have changed it, then again you have to run it. Then here you can click, you can see an option, affected properties. So review properties affected by selected model. So you have changed a model to this one, then you have to click it to see the affected properties. So you can see the two properties are affected. One is the GLMX and one is the SLMX. So the GLMX is liquid mixture molar gives free energy. Okay, we know that. Other is the SLMX. So the liquid mixture molar entropy. So this property is also affected by changing this model. Okay, so you can select the model, you can click on the affected properties and you can check which properties are affected. So the correct option is liquid mixture molar entropy. Now, which among the following will not be an affected property if the default model for estimation of vapor pure component fugacity coefficient is changed? Suppose if you change this vapor pure component fugacity coefficient, it is not given by which new model you have to change it. So you can select any other model for that, but you need to change the model for the vapor pure component fugacity coefficient, and then you need to identify which properties is not affected. Okay, so we have four options: liquid fugacity coefficient of component in a mixture, liquid pure component fugacity coefficient, liquid pure component molar Gibbs free energy, liquid pure component vapor pressure. Okay, anybody?
Option D.
Liquid pure component vapor pressure. Okay, let's see. Yeah, it's correct. So correct answer option D. Now let's go to the Aspen. So we need to change the model for vapor pure component fugacity coefficient. So which one is the model for that?
PHIV.
Yeah, PHIV. Okay. So you can see here the PHIV is the fugacity coefficient of component in a mixture. So just change it to some other model. Let make it to any random model. Okay, then run it. Okay, I'm having some error. Just go back to that method. If you see the affected properties,
It's PHIVMX, but in question it is PHIV.
sorry, it is vapor pure component fugacity coefficient.
Pure, not mixture.
Okay, okay, this PHIV. Okay, not MX. Okay, okay. Just change it to any other component. So it is the difference in PHIV is that is vapor pure component fugacity coefficient, and PHIV max is fugacity coefficient for component in a mixture. So it's for a mixture actually. So initially I selected the wrong property and model, but we need to select it this one. Okay. And if you see the affected properties, so these are the properties affected. Okay. So there is, you can see the name, which properties are going to be affected. So the vapor pure component, you can see the names. Okay. So these are the properties that are going to be affected. So here you will not see this one, the liquid pure component vapor pressure. So the option D is not affected. Is it clear, everybody? Okay. Now, which one among the following is a transport property? Viscosity, enthalpy, entropy, phase equilibrium.
Viscosity.
Viscosity.
Yes, viscosity is a transport property. And other are
Physical
Mass
property.
diffusive and
physical, okay, or thermodynamic, enthalpy, entropy.
Thermodynamic. Yes.
Yeah. Which one among the following is a thermodynamic property?
chemical potential.
Yes, chemical potential is thermodynamic property. Viscosity is a transport property. Okay. The user can neither modify nor create property method in Aspen Plus. True, false?
False.
Yes, because we can create or we can modify
False.
an existing method. Unifake is a group contribution model, but it is not predictive in nature.
False.
False.
Yes, because Unifake is predictive in nature. Which one among the following is not a Henry's component in aqueous solution in normal atmospheric condition?
NH3.
Ammonia.
Okay, why? Anybody, why?
Because it is condensable in water.
Sir, it is
Sorry,
liquid
in
at
air.
normal atmospheric condition.
It is? If what did you say? It is? Your sound was not clear.
It is liquid in
condensed.
atmospheric condition.
Okay, it is liquid in at the atmospheric condition. Okay. And the CO2, N2 and O2 will be in the vapor phase. Okay. Okay, so the answer is NS3. Henry's law is applicable with Frank Robinson, NRTL, IDLE, RK model, which?
NRTL and ideal.
Anybody?
NRTL and ideal.
Okay, NRTL and IDLE. So now we have another picture. So picture is quite a little bit blurry. I will like so the binary interaction between Henry's component and their solvent have been shown in figure. Okay. So I think one of you was having J, you were having some question regarding this binary component. So here you can see the first column, I think, is the component, and the second column, the J, is the solvent. Okay. So in that question also, in the components, that methanol and the water was not in the first list. Okay, they were like a solvent. They were in the second list. So I'm not sure this is the correct answer or not. So maybe you can check it, but as of my knowledge, I think this is the answer. Okay, but you can check it in a reference book also in detail.
Three.
So in the components we have mentioned here like AC, AN, AO, AO. In the component J, AW, AM, AW, AM, AW, AM. Okay, so basically we have, I think, is it clear to you? Picture is clear to you? Are you able to read it? Or
Yes,
should I
sir.
write it?
Yes, it will
Okay,
be 3.
Okay. So the number of Henry's
3.
components is 3 because here we can see the AC, like one component, AN, 2 component, AO, 3 component. These are the interaction between these I and J. Okay. So it's 3. The number of solvent is now the solvent. Number of solvents.
2.
2.
Yes. The solvent is 2 because if you see the solvent component J like AW, AM, AW, AM, AW, AM. So solvents are only 2. The property estimation as shown in figure 1 has been carried out using Aspen Plus version. So which version of Aspen Plus used in this estimation?
11.
11.0.
Yeah, because you can see here APV 110. So again, we have a picture. So figure 2 shows component list in Aspen plus simulation, while figure 3 shows this one, the list of components in the component group named CG1. The number of components in CG1 is, so you have given a group here, like components here, then you have a component list, component range here.
4.
So how many components will be in this range?
4.
How many?
4.
4.
4.
Because here we can see AM to AO. So AM, so the AM is here, AM is here, AO is here. So in between there are 4 components. Answer is 4. Okay, so this is all for today's class. So thank you everyone. Anybody have any doubt? Jay, is your doubt clear?
Yes, sir.
Is your doubt clear now?
Yes, sir. I tell to
Yeah,
you,
yeah.
read to your question.
Sorry.
सर फोर्थ क्वेश्चन में था
Okay,
पर
okay.
आई
Fourth
ट्राई
question. We can go to the fourth once again. So in the fourth question, if you see clearly, then you see here. So the component these are the Henry's constant, and these are the solvent. Okay. So here you see the constants will be this like Henry's component will be CO2, O2, N2, and ethane. Okay. So the methanol and water here are the solvent. They are not the Henry's component in this. Okay. Is it clear?
यस सर
Okay.
Henry's components are generally gases at room temperature, so you can remember like that also.
Yeah, yeah. And you can also consider a reference book, because I am also not expert from the chemical engineering background actually. So yeah, you can look more about this Henry's component and all the behavior in a reference book.
Ethane is a non-condensable gas, sir.
Yeah.
So can I ask a general question to you, sir?
Yeah, please.
Because I'm a chemist, I'm a doctorate, so in chemistry. So
Yeah, nice.
for my postdoctoral research work, I need to learn the software, the Aspen
Okay.
Plus. It's completely new to me. I hope you can understand, but I have to work in the software for my research work. Is it okay? Can I learn the software? Can I work with the software? With knowing some basics in chemical engineering, is it possible, sir? Because I have a doubt myself. I have a doubt myself.
No.
Can I
It's
work?
really,
Because I'm not a chemical engineer. I'm not a chemical engineer. That's why I have some fearness. Can I work with the software?
actually,
Is it possible?
I'm from mechanical engineering background, and I'm using this software like quite good a lot. Yeah, from past
Okay.
years. Yeah. So
Mm.
normally, like I only use it for my particular systems actually. So I'm working on this biogas to hydrogen systems.
Mm.
So I'm working on that domain only. So I'm also not aware of each option, each like features of the Aspen, but I know very
Okay.
well the features that are useful for me. So for you also, I
Okay.
think first in this by this course you will get to know a basic of the Aspen. Then after
Okay.
that, I think you will be able to understand like which component, which methods, which systems, which models are useful for your particular work in your research. So then you
Okay,
will
sir.
work on that particular domain, and the Aspen help is a very good section. So if you have any
Okay.
doubt, you can go to the Aspen help. So
Help
let me show
option.
you
Okay.
the Yeah. So on the right corner, you can see here.
Can I will add to Mr. Amit.
Yeah, please.
I'm Dr. Srinivas, and I did a PhD in chemical engineering, and I'm
Yes.
working at Aspen since more than 15 years.
Oh,
And
nice.
there is
Very
very
good,
one
sir.
good book. There is one good book. You can do all the drug synthesis, and you can add. You can even synthesize your components and get the basic properties from Aspen Plus. And there is one good book, and it is freely available, and it is
Oh, could you please,
thermodynamics.
sorry for the
Please
interruption, could you please say the
mention the
book
name
name,
of the
sir?
book.
It
Yeah,
would be
it will
very
be
Yeah,
good.
that
So
is
there is
thermodynamics, basics of thermodynamics through Aspen Plus by the Standler. I will share it in the group chart. I think it's
yeah,
available
there is a
in this.
Q&A. So you can see this
please,
Q&A
please
is
share
there.
it, sir. Thank you so much.
So please
It's very
write in
good
the
book, and whatever
Q&A.
Mr. Amit and Professor is telling, all the details are there in that book and very clearly
Okay.
explained and with version 12, and that is freely available in ResearchGate website. I will share the link also. You can download it
Okay.
and you can try
Okay.
all the methods. And it is very useful for everybody and to
So
even Amit
where can I,
also. It is very
in
Yeah,
good book.
question
thank
and
you.
answer
Thank you.
option, I can see. Okay, I can see the link, your link.
So there is
Okay.
a Q&A. So please put
Okay.
your link here. So it
Okay.
will be good. Okay.
Thank you very much, sir, for sharing the information.
Yeah, I
Because
think in this Q
I'm
in this
asking the
Q&A
question
you will
because
also get. I think there is a Q&A. There is a
It's
link
in my
of also for the
laptop, so
WhatsApp group. Yeah.
I will put it separately later, I think.
Yeah,
Is there
sure, sure.
any?
Maybe there is a group also. You can put in the group also, or yeah, no issue.
Okay, I will open the course website and put it there. I think I can put
Yeah,
it there.
yeah, sure,
Okay,
sure.
I will keep that link. It's a very good book.
where can I see
Okay.
the link, sir? Sorry, I have a doubt. Where can I see the link in the course website?
Maybe I think he's
NPTEL
about to.
website.
Yeah, NPTEL.
Sorry?
There is, I think the course form is there. So in that course form,
Yeah,
you can
course
discuss.
forum
This
is there.
discussion form is there. Yeah,
I will add
forum is
there.
there.
Yes.
Yeah. So he's going to
Okay.
add the link there, so you can refer to that link.
Thank you very much, sir. If you know any other books to know the basics in chemical engineering for a chemist, for
If you,
non-chemical
yeah,
engineering students, could you please suggest the book as well
yeah,
to
actually,
know?
if you go to this course link also, so in that link, the professor has also specified some reference books. So you can
Okay.
also take help from those reference books also. Yeah,
Can I
just
download the
visit.
books?
Download, I don't aware because I don't, maybe they are freely available. I don't know that thing, but maybe like if you are working in an institute, then I think you will be having sure the subscription to the institute library. So I think you will
Because
get those books. Yeah.
sorry for the interruption, sir, because I'm searching for some books to learn some basics in chemical engineering as well as in the Aspen Plus software, but I couldn't download the books, any books. It's not freely available. That's why I'm asking you.
So actually, I'm not aware of this. You need to refer some library or some institute. So in that case, I can't help you. But now
Okay.
you just try it, Google search, or nowadays ChatGPT is also there. You can take help from ChatGPT. Maybe that is like they provide you some links and all, so you can refer that. So
Okay.
okay.
Is there
Thank you
any
everyone
other?
for
Okay, thank you. Thank you so much. Is there
yeah.
anyone who knows any other books,
I think
references?
it's
Please, you can
better.
share your link to
I
us.
think it's better if you like ask this question on the course forum, because here we have only 12 participants now. So if you put your like if you have any query, you can put it there. Maybe
Okay.
because in the course there are multiple, like I think more than 100 or like 200-300 participants are there. So maybe they will give you a more better answer.
Okay.
Okay.
Thank you. Thank you very
Okay.
much.
Okay. Thank you everyone. Thank you for joining. Thank you. Bye bye.
Thank you.
Bye,
Thank you.
sir.
Bye.
Thank you.